Hello everyone. Please tell me whether audio and video is clear or not. Good evening guys. Good evening. So tell me whether audio and video is clear or not. Please tell me guys whether audio and video is clear or not. Okay, it's clear. Okay, thank you. So maybe let's share these videos, share this video so that everybody can join. Okay, give me 2 minutes so that I can share on the channels, on Telegram groups. Okay, you can also share this video to the Telegram group so that other students can also join this session. Okay, so in this session again we will discuss about eigenvalue and eigenvector, because if you remember in the previous class we were discussing about eigenvalues and eigenvector, and in this session also we will continue that part. So in the previous session I told you about linearly dependent and linearly independent eigenvectors. Okay, so in today's session we will discuss more about dependent and independent and diagonalization, and how to check whether the eigenvector will be linearly dependent or independent, and what is the relation of rank with dependency. Okay, how to calculate rank of a matrix, that we will discuss, and what is the relation of rank with linearly dependent and independent eigenvector, we will discuss that, and moreover how to check that. And also we will discuss about diagonalization, how to diagonalize a matrix. Okay, so we will discuss that. Why I'm teaching you, because this is important as far as control system is concerned. So in control system you will understand the diagonalization meaning, especially in state space. That's why I'm teaching you this part. Okay, so let's complete the introduction part first so that student can join in the meantime. Okay, so this is my introduction guys, and my name is Asu Jangna. I teach almost every subject, so you can join your preparation with me, and you can join BYJU'S exam prep platform to start your preparation. Okay, and there is one workshop which will be on 7th of May, which is tomorrow. So you can join this workshop. This workshop will be at 12:30 p.m. and this workshop will be taken by Rasul Chotani. He secured All India rank 12, so you can join with him and get the idea how to crack GATE 2023-2024. Okay, so you can join this, and moreover 2024 rather. Okay, so you can join this workshop, you can register this workshop, the link is given in the description. Okay, okay guys, so now it's time to start. Okay, LE 222, sir, I am new one, does I understand? Little bit you will understand. Okay, little bit, but not up to that mark, because it is in the continuity of the previous class. If you have attended the previous class you can easily understand, but if you have not attended, little bit difficulty you will face. Okay, so first of all I want to discuss you with the rank. Okay, rank of a matrix. Rank of a matrix. First of all we will discuss about a rank of a matrix. Rank of a matrix, we will discuss that. Rank of a matrix, how to calculate a rank of a matrix, and what is the physical significance of rank, why we calculate rank. Okay, for that we need to understand span. First we need to understand span of vectors. Span, what is span? First we need to understand span of vectors. Once we get the idea of span, then span means rank. The mathematical picture which capture this span is rank. Okay, so how to determine the span? Let's say we have two vector. One vector is v1 like this and v2 like this. Okay, let's say there are two vector v1 and v2. Now if you are taking the linear combination of these two vectors, let's say you are taking a v1 plus b v2. A and b are constants. A and b are constant. They can be positive, negative, fractional, integer. Okay, so a and b are constants. You can take a and b, it's your choice. Whatever value of a and b you want to select, you can select. Okay, so if you take linear combination of v1 and v2, then you can reach at every point in this space, at every point in this 2D, every point in this 2D plane. It's not in space, every point in this 2D plane. You can reach at every point in this 2D plane. It means the span of these two vectors is 2D plane, is 2D. So span is 2D. Span is 2 dimension. Okay. If you, let's say A is 1 and B is also 1, then if you take 1 V1 plus 1 V2, then the resultant will be somewhere here. So if you want to reach at this point, then also you can reach by adjusting A and B, you can reach at this point. Okay. You can reach at this point. At any point you can reach using the combination. Okay. So we call it span. But let's assume that the two vectors are in the same direction. Let's say V1 is in this direction and V2 also in this direction. Both V1 and V2 are in this same direction. Now, if you take linear combination of these two vectors, BV2, then you can only move on the line. You can only move on the line. Okay. So the span is 1D. The span is 1D. Okay. One dimension means line. The span is 1D or line, simple line you can say. Okay. Here the span was 2D, two-dimensional span. Okay. Plane. The span in this case was plane. In this case, the span is line. Okay. It means in this situation, whatever A or B you take, the resultant vector will lie on this line itself. That's why you can only move on this line with the help of linear combination of V1 and V2. You can only move on this line. Okay. So the span is line only. Now what you can do is, what is the difference between V1, V2 and V1, V2 in these two situations? You can see that here in this case, you cannot represent V2 in terms of V1. They are independent. You cannot represent V2 in terms of V1. But in this situation, you can represent V2 in terms of V1. You can say that V2 is a double or maybe 1.5 times of V1. V2 is 1.5 times of V1. You can say that. It means you can represent V2 in terms of V1. Similarly, you can represent V1 in terms of V2. You can say that V1 is 2/3 of V2. Simple. It means in this case, V1 and V2, you can represent V1 in terms of V2 or V2 in terms of V1. But in this case, you can't say that. You cannot represent V2 in terms of V1 because they have different directions. So in this case, these two vectors are linearly independent. Linearly independent. Linearly independent. And in this case, V1 and V2 are linearly dependent. Linearly dependent. Okay, you have to understand what is the meaning of linearly independent and dependent. Okay, so in this case, these two vectors are linearly independent. You cannot represent V2 in terms of V1 or V1 in terms of V2, but in this case, you can represent V2 in terms of V1 and V1 in terms of V2. So they are linearly dependent and they are linearly independent. What does it mean? How to check whether the vectors are linearly dependent or independent? How to check that? Let's say we have two vectors. So with the help of two vectors, if we have two vectors, let's say V1 and V2, two vectors. Let's say we have V1 and V2. And let's say V1 is in this direction and V2 is in this direction. Let's say V1 and V2 are like this. V1 is in this direction and V2 is in this direction. Now, the maximum span they can attain. The maximum span means the span of these two vectors. It can be 2D. It can be 2D. And if they are in the same direction, it can be 1D. So first you have to check the span. What is the span can be, the maximum value of the span, 2D or 3D or 1D, that can be calculated with the number of vectors. If there are two vectors, it means the span, maximum span can be 2D. In the best case, the span will be 2D. And in the worst case, the span will be 1D. Okay? I hope it is clear. Now, since in the best case, the maximum span can be 2D, the biggest span that they can have is 2D. If the actual span is less than the maximum value, less than this maximum value 2D, if actual span is less than that, it means they are linearly dependent. It's a simple idea. You can remember like this. Okay, it's a trick you can say. We know that there are two vectors, so number is 2 now. the number of these two vectors is 2. There are 2 vectors, so maximum span they can have, make is 2D. But actual span, the actual span in this case is again 2D. But if let's say these two vectors are in this way, v1 and v2, then since there are 2 vectors, so the maximum span they can attain is 2D, but the actual span they have is 1D, a single line. If you take linear combination of these 2 vectors, they can only the resultant can only move on the line. So actual span is 1D. So if actual span is less than the maximum span they can attain, we call linearly dependent. So these 2 vectors are linearly dependent. Now let's take one more example. Let's say I have 3 vectors, 1, 2, and let's say 3. v1, v2, and v3. So now you can see that all these 3 vectors are in same plane. This third vector is in the plane of the previous 2. This third vector is in the plane of previous 2. Now, if you take the linear combination of these 3 vectors, can you tell me what is the span? At what point you can reach? Can you reach at this point outside the plane? Okay, let's say I take a point here in space. It's not in this plane, it's outside the plane. So can you reach at this point using the linear combination of these 3 vectors? Answer is no. You can only reach to the point which is on this plane. At that point you can reach. It means, so the span of these vectors is, so span, tell me, span is 2D. But the number of vectors are 3. 3 is more than 2. The number of vectors is 3. It means the maximum possible span they could have is 3. But in this particular situation, actual span is 2D. It's less than 3. So they are linearly dependent. You can say that they are linearly dependent. Linearly dependent. Okay, you can say like this, linearly dependent. So first you have to check. What is the number of vectors. The number of vectors is 3. It means the maximum span they can have is 3D. But in particular situation, the span is not 3D. Since the third vector is in the plane of the previous 2, if you take the linear combination, the resultant will always lie in the plane of these vectors. It means the span is 2D, which is less than 3. So they are linearly dependent. Or simply you can say that this vector is a redundant vector. Because this third vector is in the plane of the previous 2, so you can represent this third vector as a combination of v1 and v2. So actually you don't need this third vector. This third vector is lying in the span of the previous 2. It means it's not changing the span. It's not changing the span of the previous 2 vectors. For previous 2 vectors, the span was 2D. If I add one more vector, third vector, then it is not changing the span of the previous 2 vector. It means the span remains 2D if you add this third vector, because the third vector is already in the plane of the previous 2. Okay, now let's take one more case. Let's say there are 2 vectors. V1 is this, V2 is this, and if I want to take third vector, let's say, if I want to take third vector, and third vector is not in the plane. The third vector is somewhere in the space like this, okay? Somewhere like this, or maybe perpendicular to this plane. Okay, the third vector is in this direction, v3. So v3 is in this direction, in your direction, outside. Now you cannot represent v3 in terms of v1 and v2. Similarly, you cannot represent v1 in terms of v2 and v3. Similarly, you cannot represent v2 in terms of v1 and v3, because v3 is in third direction. Now the span will be 3D. Now the span will be 3D. Okay, if you take linear combination AV1 plus BV2 plus CV3, then you can reach at any point in the space. You can reach at any point in the space. Okay, it means the span of the 3 vectors is now 3D, and the number of vectors is also 3. So they are linearly independent vector. They are linearly independent vector. Independent vector. They are linearly independent vector. I hope it is clear. So it means you can check whether the vectors are linearly dependent or independent by checking the number of the vectors and the span. If span is less than the number of vector, you can say that they will be linearly dependent or independent. Now this span is captured by rank. because it will not be possible to always check the span like this, because this is a qualitative analysis. Now we need to check quantitative analysis. We have to do some mathematical tool. I mean, we must have some mathematical tool. Using that mathematical tool, we can check the span. Now this span information is captured by rank. If you know how to calculate the rank of a matrix, it means you know the span. Let's say we have a matrix. Let's say I have a matrix 1, 4, 2, 8. Let's say I have a matrix like this. Now this matrix represents two vectors. One vector is this, I call it V1 and I call it V2. So there are actually two vectors. You can represent the vector like this. Okay, every column represents vectors. So there are two vectors. Now it means the rank will tell you about the span of these vectors. The rank will tell you about the span of these vectors. Now what is the rank of this matrix by which you can calculate the span? If the span is less than the number of vectors, then they will be linearly dependent. Otherwise, they will be linearly independent. Simple way. Okay. Simply you can calculate like this. So if any matrix is provided to you, let's not call it A, let's call it some matrix V. Okay. So it's a matrix V. Okay. In which this first column is V1, the second column is V2. So it has two vectors. Now we need to calculate rank. If rank of this matrix, if rank of this matrix is 2, let's say, it means the span is 2D. And the number of vector is also 2. So they are equal. If they are equal, they will be linearly independent. But if rank or span of this matrix is less than 2, because there are two vectors now. So if the rank is less than 2, it means the span is less than 2. So they are linearly dependent. Simple. Okay. Simple. Sir, when will network theory in English you will resume on YouTube? Yes, we will resume, Abdul, don't worry. We will resume it soon. Okay. We will resume network theory also, because the problem was with the number of students. Okay. So that was the problem, because the number of students who are watching live were very less. Okay. That's why we have to stop that. Anyway, we will continue that. We'll resume that. Okay. Let's come back to this. So I told you what is the meaning of rank. So now how to calculate the rank? If you know how to calculate the rank, then you can easily say that the rank of this matrix is 1. Rank of this matrix is 1. How to calculate rank? It's, I mean, there is a method to calculate rank. Let me tell you a simple method. Let's say I have a matrix. 1, 2, 4, 5, 6, 7. Let's say this is the matrix. So now you can see that the order of the matrix is 3 row, 2 column. This is the order of the matrix. Okay. Now we need to calculate rank. How to calculate rank? First of all, rank is defined for square matrix. Rank is defined for square matrix. So first thing is, you can capture 2 by 2, the biggest square matrix from this matrix. I mean, you have to make the subset of this bigger matrix. And that subset has to be square matrix. And the biggest square matrix you can capture from this matrix is 2 by 2 matrix. Okay, so you have to break this matrix into 2 by 2 matrices. So tell me, it's a 3 by 2 matrix. So if you want to break it, you can have many 2 by 2 matrices like this. 1, 2, 4, 5. So you can capture this matrix only. It's a 2 by 2 matrix. Now you can also capture this matrix. It's again 2 by 2, 4, 5, 6, 7. This is again 2 by 2. Or what you can do is you can take this row and this row. Okay. So 1, 2, 6, 7. Okay. So this way you can make all possible 2 by 2 matrices. All possible 2 by 2, because we have to go to the square matrix. This is not a square matrix. So we have to go to the square matrix. So we can capture first the square matrices like this. Once you get the square matrix, then what will happen? Tell me. Once you get the square matrix, then what you can do? You can calculate the determinant. This is 2 by 2, this is 2 by 2, this is 2 by 2. Okay. You can calculate the determinant of this matrix. So determinant of this matrix is not equal to 0. Okay. Determinant of this matrix you have to check, and check whether the determinant of this matrix is 0 or not. Okay. So you have to check the determinant of this matrix. So determinant of this matrix is, you can say 5 minus 8. This is equal to minus 3. It is not equal to 0. If determinant is not equal to 0, if any one matrix has non-zero determinant, then you can say the rank is 2. Then you can say that the rank is 2. But if the determinant of all the matrices are equal to 0, then rank cannot be 0. Rank cannot be 2. Rank cannot be 2. You have to go to rank 1. Okay. So this way you can check the rank. There can be multiple way. I have this method. I mean, this method suits me because it's simple for me, because I can directly check the determinant, and I can say that if it is not 0, the rank is 2. Rank cannot be 3. For this matrix, rank cannot be 3. Why not? Because it's not 3 by 3 matrix. You can't make it 3 by 3, but you can make 2 by 2. Because you can remove one row, but you can't add one column. Because one column is unknown, you can't add it, but you can remove row, because you already know the row, then you can already, you can remove that row. There is no problem at all, okay? So row can be removed, but column cannot be added. That's why the maximum possible square matrix is 2 by 2. So you can make 2 by 2 matrices like this. Possible 2 by 2 matrices are like this, okay? Now if you know these 2 by 2 matrices, then what you can do is you can calculate the determinant. If anyone has non-zero determinant, you can say that the rank is 2. But if all the matrices has 0 determinant, all possible 2 by 2 matrices has 0 determinant, it means rank cannot be 2. You have to switch to the lower order, okay? So the rank can be 1 or 0, okay? So you have to check again for 1 by 1 matrices, okay? I hope it is clear. Let's take one example. And how to calculate rank first, and then I will come back to span and linearly dependency. Okay, let's say I have a matrix S. And the S matrix is like this: 1, 2, 2, 1, 4, 5, and 2, 6, 7. Let's say this is the matrix we have. So you know that it's a square matrix. So the maximum possible rank is 3. Maximum rank you can attain is 3 or 2 or 1. 0 is not possible. Why not? Because for 0 all the element has to be 0. It has to be null space, okay? Then only the rank will be 0. So 0 is not possible. So let's remove this 0 part, okay? So now the rank can be 3, 2 or 1. And the biggest square matrix we have 3 by 3. This is the only 3 by 3 matrix. So the possible rank can be 3. But is it 3? I mean, you have to check. How to check? Check by its determinant. So the determinant of this S matrix, you can see that determinant of S is 0. You can calculate, and the determinant is 0. If the determinant is 0, it means the rank cannot be 3. Rank cannot be 3. It cannot be 3. You have to go to 2. Rank can be 2 or 1. You have to check for rank 2 or rank 1. Okay, now how to check for rank 2 or rank 1? You have to take out 2 by 2 matrices. Possible 2 by 2 matrices. So let's take this 2 by 2 matrix. 1, 2, 1, 4. And you can see that the determinant of this matrix is 4 minus 2. That is equal to 2, which is not equal to 0. So the determinant of this matrix is non-zero. If the determinant of this matrix, if any 2 by 2 matrix determinant is non-zero, so you can say that rank is 2. Okay. So now rank is 2. Okay. So now this way you can calculate the rank. So it's easy for me. It's easy for me. It's easy for you also to check this way. Any 2 by 2 matrix got non-zero determinant, okay, then the rank is 2. But if all the 2 by 2, all possible 2 by 2 matrices, if you track from this, and all 2 by 2 matrices have determinant 0, then rank cannot be 2. You have to switch to 1 by 1 element. Okay. I hope it is clear how to calculate rank. For this matrix, the rank is 2. It means the span. Let's say this is the vector v1, this is vector v2, this is vector v3. This represents vector v1, this represents vector v2, and this represents vector v3. So there are 3 vectors, and the span is 2. So now you can say that these 3 vectors are linearly dependent. Okay. Sir, why not rank 3? Because its determinant is 0. You can check that. You can check that its determinant is 0. Since its determinant is 0, rank cannot be 3. I told you, na? Because all 3 by 3 only one 3 by 3 matrix is possible. This is the only one 3 by 3 matrix. If all 3 by 3 matrices have 0 determinant, rank cannot be 3. So now you have to go to 2 by 2 matrices. So I have selected this 2 by 2 matrix first, and I got non-zero determinant. If you got non-zero determinant, you don't need to check other 2 by 2 matrices. If anyone has non-zero determinant, the rank is equal to 2. You can directly say that the rank is 2. Okay. So that's why the span is 2. But the actual vectors are 3. There are 3 vectors, and the span is 2. It means these three vectors are linearly dependent. It means these three vectors are actually, they are in the same plane because their span is 2D. Okay, their span is 2D. Rank is 2 means span is 2D. It means they are in the same plane. That's why their span is 2D. And they are dependent. Why they are dependent? Because if they are in the same plane, then what you can do is you can represent any vector as a combination of the other two vectors. You can represent V3 as a combination of V1 and V2. You can represent V1 as a combination of V2 and V3. Similarly, you can say V2 as a combination of V1 and V3. So it means any vector can be represented as a combination of the other two vectors. So they are dependent, linearly dependent. I hope it is clear how to check whether the vectors are linearly dependent or independent with the help of rank. So with the help of rank, you can check the dependency. With the help of rank, you can check the dependency. Okay. So these vectors are linearly dependent. Okay. I hope it is clear. So I told you about rank. Rank is related with span, and span is related with linearly dependent and independent vector. I hope it is clear. Okay. Now let's move ahead. In the previous class, I told you about eigenvectors. I told you about eigenvalues and eigenvector. I told you that let's say there is some vector V, and if you apply a linear transformation and you get the same vector V with some factor lambda, with some scaling factor lambda, we call this vector V as eigenvector. This V is known as eigenvector. Okay. This is known as eigenvector. Okay. This V is known as eigenvector, and lambda is known as eigenvalue. Lambda is known as eigenvalue. Okay. V is eigenvector and lambda is known as eigenvector. Now, what about this vector? We have to discuss more about this eigenvector. In the previous class, I told you how to calculate eigenvector. Now, the eigenvectors will be linearly dependent or independent. We have to check that. If eigenvalues are distinct, you have different eigenvalues. Let's say you have a 3 by 3 matrices. Okay. Let's say there is a matrix which is 3 by 3, A, B, C, D, E, F, G, H, I. Let's say it's a 3 by 3 matrix and the eigenvalues are distinct, lambda 1, lambda 2, lambda 3. If you have distinct eigenvalues, it means the scaling factor are different. Then you must have independent eigenvector. Then eigenvector will be linearly independent. Eigenvector will be linearly independent. Linearly independent. Then the eigenvector will be linearly independent if you have distinct eigenvalues. Remember this point. If you have distinct eigenvalues, eigenvector will be linearly independent. You will have linearly independent eigenvalues, eigenvector. Okay. But if lambda is repeated, if eigenvalues are repeated, then it may be possible that eigenvector are linearly dependent or linearly independent. It means in this case, you may have linearly dependent eigenvector as well as linearly independent eigenvector. You have to check. If lambda is repeated means, let's say you have a matrix A, and for this A matrix, it's a 3 by 3 matrix. Now for this matrix, let's say the eigenvalues are lambda 1, lambda 2, lambda 2. It means there are 3 eigenvalues, but out of these 3, 2 are repeating. 2 values are repeated. Okay. Now for this eigenvector is V1, for this eigenvector is V2, but for this eigenvector, let's say V3. Now since they are repeated, so it may be possible that these 3 eigenvectors are linearly dependent or independent. You have to check. You have to check whether these 3 vectors are linearly dependent or independent. Now how to check? How to check whether these 3 vectors are linearly dependent or independent? It's very simple. How to do that? Using AM and ZM. Now I'm not going to tell you about the proof of this. But using AM and ZM, you can check whether these three vectors are linearly dependent or independent. Okay, what is AM? AM means arithmetic multiplicity. Arithmetic multiplicity. What is ZM? ZM is geometric multiplicity. Geometric multiplicity. Now, how to calculate that? How to calculate arithmetic multiplicity and geometric multiplicity? If arithmetic multiplicity is equal to geometric multiplicity, then eigenvector will be independent. Eigenvector will be linearly independent. Will be linearly independent. Okay? Independent. If AM equal to ZM, then eigenvector will be linearly independent. But if AM is not equal to ZM, if AM is not equal to ZM, then eigenvector will be linearly dependent. Then eigenvector will be linearly dependent. Linearly dependent. So you have to check whether AM and ZM are equal or unequal. Now, how to calculate AM and ZM? How to calculate arithmetic multiplicity and geometric multiplicity? It's very simple. Okay, let's take a matrix. Let's say I have a matrix A. A is equal to 2, minus 1, 2, 0. Let's say we have this matrix A. Now, if you calculate eigenvalues of this matrix, lambda 1 equal to 2 and lambda 2 will also be equal to 2. So you have same eigenvalues. You have same eigenvalues. Now we need to comment on eigenvector, whether the eigenvector will be linearly dependent or independent. For this eigenvector, let's say V1, and for this eigenvector, let's say V2. Now we need to check whether these two vectors are linearly dependent or independent. Now how to check? How to check? Let's calculate AM and ZM. Okay, now you can see that lambda is repeated twice. So arithmetic multiplicity is 2. Arithmetic multiplicity means how many times this lambda is repeated. Okay, so you can see that this lambda 2 is repeated twice. It means the arithmetic multiplicity is 2. Now, what about geometric multiplicity? So geometric multiplicity you have to remember, and that is equal to n minus rank of a minus lambda I. A minus lambda I. N means dimension of the matrix. What is the order of the matrix? Okay, order. It is order of the matrix. So if you calculate ZM, then ZM will be equal to geometric multiplicity will be equal to, what is the order? Order is 2 by 2. So 2, order is 2 minus a rank of A minus lambda. Lambda is 2 because we are calculating calculating geometric multiplicity for eigenvalue which is repeating. The eigenvalues which is repeating, for that value we are calculating the geometric multiplicity. So geometric multiplicity will be order. Order is 2 minus rank of A minus 2i. A minus 2i. Okay, that will be my geometric multiplicity. Now how to calculate that? How to calculate the rank of this? You know how to calculate rank. Okay, first let's calculate A minus 2i. So A minus 2i will be equal to, I can write it directly. A minus 2i will be equal to 0, 0 and minus 1, 0. Okay, so this is minus A minus 2i. Now the rank of this matrix is, what is the rank? Rank is 1. Okay, it cannot be 2 because the determinant of this matrix is 0. So if the determinant is 0, it means rank cannot be 2. So you have to go to rank 1. I mean single element. Now one element is non-zero. If one element is non-zero, it means rank has to be 1. Okay, so rank is 1. So now this rank is 1. So if I put this rank, so geometric multiplicity will be equal to, tell me what is geometric multiplicity? That will be equal to 2 minus 1. And 2 minus 1 is 1. Arithmetic multiplicity was 2 and geometric multiplicity is 1. It means they are not equal. If they are not equal, what does it mean? It means the eigenvector will be linearly dependent. They will be linearly dependent. You can't have linearly independent eigenvector. Okay, so eigenvector V1 and V2 will be linearly dependent. V1, V2, V1 and V2 linearly dependent. What is the meaning of this? If two vectors are linearly dependent, it means the span cannot be 2D. The span has to be line. Span has to be a single line. It means these two vectors are in the same direction. Okay, so they are linearly dependent vector. I hope it is clear. Okay, so this way you can check AM and GM. With the help of AM and GM, you can check whether the vectors are linearly dependent or independent. And there is one more advantage of this AM and GM, and that is diagonalization. Sometimes what you need to diagonalize a matrix. Let's say you have a matrix A and we need to diagonalize. We need to diagonalize this matrix. How to diagonalize it? The diagonalization method is very simple. What you need to do is, first you have to calculate eigenvector. Let's say this A matrix is a 3 by 3 matrix. It's a 3 by 3 matrix. So the eigenvalues are, let's say, lambda 1, lambda 2, lambda 3. Distinct eigenvalues are there. If they have distinct eigenvalue, if this matrix has distinct eigenvalues, so the eigenvector will be linearly independent. So they are linearly independent. V1, V2, V3. So we found eigenvector V1, V2, V3. Now what we have done is we found an eigenvector matrix. This is eigenvector matrix. Eigenvector matrix. Now how to represent this? How to find this eigenvector matrix S? This eigenvector matrix is very simple. You can write it like this: V1, V2, V3. Means every column represent a vector. Every column represent a vector. So this is my eigenvector matrix. Let's say V1 is 1, 0, 2. V2 is 1, minus 1, 2. And V3 is, let's say, 3, minus 6, 8. Let's say there are 3 vectors. These are the eigenvectors corresponding to these eigenvalues. Now they are linearly independent, let's say, because these values are distinct. If these values are distinct, then the eigenvector will also be linearly dependent, okay, linearly independent, okay. So now what we can do is we can make the eigenvector matrix like this. The first column is represented by this. The second column is represented by this, okay. And the third column is represented by this. 3, minus 6, 8. So this is my eigenvector matrix. Once you get this eigenvector matrix, now you can simply diagonalize this matrix A. This A can be diagonalized now. How to diagonalize this A? It's very simple. There is a process to diagonalization. I don't want to prove that, okay? The proof is very easy. You can prove, okay, if you want to calculate the diagonal matrix, then to find the diagonal matrix, this will be S inverse AS. It means you have to pre-multiply this A matrix with S inverse. S is this eigenvector matrix. Okay, you have to pre-multiply with S inverse and post-multiply with S. Okay, this way you can diagonalize it. And let me tell you guys, the answer will be lambda 1, 0, 0, 0, lambda 2, 0, and 0, 0, lambda 3. It means if you are transforming the vector A into its diagonal form, if you are applying similarity transformation, and if you are diagonalizing a matrix A, then that diagonal matrix will contain the eigenvalues on its principal diagonal. Okay, so you can represent the eigenvalues on its principal diagonal. Is it clear, guys? So this way we can say that we have this matrix. This is the diagonal matrix we have. I hope it is clear. So whenever you need to diagonalize, you can apply this method. You have to first calculate this, and then you can diagonalize this. You can apply this method. But here, one catch. You can't diagonalize every matrix. You can't diagonalize every matrix. Some matrices are not diagonalizable. How to check whether the matrix is diagonalizable or not? To check, what you can do is, you can check eigenvector. If these eigenvectors are linearly dependent, you can't diagonalize. It means this S matrix. In this S matrix, these eigenvectors are linearly dependent. It means one vector is a combination of the other two vectors. It means you can't calculate its inverse. Why? Because its rank cannot be 3. They are linearly dependent. If they are linearly dependent, these vectors are linearly dependent. What does it mean? It means its rank cannot be 3. Its rank has to be 2 or 1. If its rank is 2 or 1, what does it mean? It means they are linearly dependent. So if they are linearly dependent, the determinant of this matrix has to be 0. It means you can't calculate this S inverse. so you can't diagonalize. Okay, so it means what you can do is you can remember like this: if you have dependent eigenvector, if you have linearly dependent eigenvector, you can't diagonalize. This matrix will not be diagonalizable. You can't diagonalize, you can't find S inverse, you can't diagonalize. Okay, but if you have linearly independent eigenvalues, you can always diagonalize. And after diagonalization, the answer will be like this. It's easy peasy. Okay, so you have to remember this. I hope it is clear. Now to check whether the matrix, whether this matrix is diagonalizable or not, you can directly calculate AM and GM. With the help of AM and GM, you can check whether the vectors are linearly dependent or independent. If AM is equal to GM, what does it mean? It means matrix is diagonalizable. Eigenvector will be independent. The matrix will be diagonalizable. If they are not equal, it means the matrix is the vectors are linearly dependent. It means you can't diagonalize it. Simple. Okay. I hope it is clear, guys. Okay. So with the help of AM and GM, you can check whether the matrix is diagonalizable or non-diagonalizable, whether you can diagonalize it, whether you can apply similarity transformation on it, especially the diagonalization process. So it will be possible only if eigenvectors are linearly independent, and that can be checked with the help of AM and GM. I hope it is clear to everyone. So let's stop it here. Okay, so in today's session, we will discuss only this part. I hope you enjoyed this session. So this was all about mathematics, eigenvalues and eigenvector. So in the next class, we will discuss about logarithmic scale. That is again very important. Okay, so you have to attend that class also. That class will be on Monday. So see you on Monday, guys. Okay, I hope you enjoyed this session. Don't forget to like this session and press the bell icon so that you get the notification whenever my sessions will be live. And don't forget to subscribe our channel. We have our mobile app, so you can install this mobile app. Go to the Google Play Store and install our mobile app. There also you'll find free lectures, and I'm also taking free lectures on our mobile app, so you can join those lectures also. Okay, guys, so that's all for today's session. Thank you and take care. Bye.